All right, good evening, everyone. As you can tell, it's night at my place. I still haven't figured out how to get the lighting to work, and I think at this point, I'm just going to have to accept what this is. Mostly, what I want to do is I want to be able to have class asynchronously for us. I want you to be able to ask questions, and then I want to be able to answer them. Sometimes we do this in person, sometimes we do this online and asynchronously. The nice thing about doing it this way is I can actually look up little things that I've written that answer your questions in other ways and point you in certain directions. When I do that, that means if you still have questions after that, you can actually go into that reference. And I'm going to give you one particular reference that really is outside the scope of this class, but I think that the questions that you're asking are very important. And so there is more to tell. But let me just point you in that direction. And it started on the wrong thing. There we go. We're covering chapters 1 through 3 of A World from Dust. This is your questions and student questions that we have. And so I'm just going to read through the questions, and then I'll answer them as best as I can. So one question is that, the whole story is that we're starting with an Earth that was inhospitable to life. Toxic gases. It changed to a place where humans and living organisms could live. There's still places like Mono Lake. We start there, in a sense, because Mono Lake is one picture of what the Earth may have looked like before there were chemicals that it could use to better advantage. And Mono Lake even is still an oxygen environment. The most important thing is that non-oxygen environments are the truly ancient ones. We can find those environments as well. They've just retreated because oxygen has sort of crowded them out. So the question is a very good one that often comes up with things like this. Why is it that we can still find places that are naturally toxic for humans? Well, part of that is because it's still the exception that there are places where humans can live, especially without technology. As a human, if you couldn't have a spacesuit, you can't go into space. If you don't have a diving suit, you can't go under the water. And in fact, if you don't have a warm jacket, you can't go very far north. So there's actually a limited set still where humans can live. We're kind of weak animals when it comes to the conditions we can tolerate. But the difference for us is that we can actually use our hands and use our brains to make technology that allows us to explore these other places. They're still ultimately inhospitable to us, but we have made ourselves stronger to be able to visit them. We haven't necessarily changed the places, we've changed us. And so but the question of why are there so many places where we could live at all, one of the answers is actually a very deep concept that's important for this whole book. It's the concept of coevolution. One of the things you might have noticed is that there's mineral evolution as well as animal evolution. And yeah, they're different things, and some people may question, does evolution even really apply to both of them? I think it does. It looks different in both places, and it might have different elements and different mechanisms, to be sure. But I do think that the change over time of mineral evolution has something to say to the animal evolution, and they actually did allow each other to continue. Especially the mineral evolution opened up ways for animal evolution to be able to take place. But because of that, because there was a whole process, there are places where the process didn't happen as much. Those are the places that you're talking about with this question. So I could kind of flip the question around. It's kind of like, why are there so many places that are non-toxic for humans, rather than why are there so many places that are still naturally toxic, but we have made the non-toxic places less toxic, more hospitable, if by allowing us, by our technology that turns arid land into places that will grow farming for us. Agricultural science is actually one big answer to this question, because a lot of it is the art of turning something inhospitable to something more hospitable. There's still chemical keys to that. You have to have water to be able to do that. You have to have the sunlight that you need. You have to have temperatures that you need. And now we're reaching the point where we may have not considered things Like now you don't have the temperatures that you need anymore if we put too much CO2. If our tech puts too much CO2 into the atmosphere, it might mess up the places that we've been able to advance to. We've got to consider the whole system and the whole Earth and our role not as people to take what we want out of it, but to co-evolve along with it, to consider the animals, to consider all the other systems that we are living with. It's actually a kind of environmental kind of way of looking at things. The fact that evolution is actually going on, not just in the animal kingdom, but also for the vegetables, of course, but even minerals. Everything is changing, and we are able to figure out how to change along with that. We've got to make sure that we don't disrupt these environments and make more toxic environments with our own tech. It's a very interesting question. I want you to keep thinking about this as we go along. So the next question is about this figure. I believe this is figure 3.3. And it's the abundance of the elements for life for the whole universe. And notice a few things about this. It's a log scale, for one thing. That means there's still a ton of hydrogen and helium. And there's only a little bit of the things at the very bottom. So the question is, I'm going to have a better view of this image so I can talk about it better. But a lot of the things that are toxic are ones that are below the line because there haven't been enough of it for us to be exposed to it. If there was more time, could life evolve with different fundamental chemistries other than carbon? Because carbon's really high on this graph right here. In fact, let me show you the graph and let me condense the question. Given time or with a different base element than carbon, could life have been based on a different set of elements? And so it's the idea of, in one sense, yes. In a minor sense, yes, I would say, but in a major sense, no. So the minor sense in which I'll say yes is that we're even seeing this happen. There's places where cadmium has replaced zinc in certain enzymes. There's the idea that if the element is around, now it needs to be around for hundreds of thousands of years for life to really adapt to it, and it has to be prevalent for that long. So some of these elements below the line could come above the line as life sort of evolves with them. Now, for them to be made in stars and then to be ejected into planets and things like that, that would take billions and billions of years. It's possible the universe will run out of juice before any of those elements are able to become prevalent enough for them to even be approached by life. And of course, we're now in an artificial situation rather than a natural situation. This whole question is based on a natural situation. So that's the back and forth about all of that. Maybe if the universe was able to age to be 100 billion years old, you could have some of these things opening up. But then if you already had a chemical system that worked well based on carbon, it would have to actually outclass that chemical system to be able to overtake it. So that's why I'm saying in a major way, I don't think you could. Because even if you had more time, you would still have the carbon around, and the carbon works very well. So it's unlikely that a new coming element would be able to do this. And even looking up and down, you'd have to go pretty far down. There's even an argument that there's nothing like carbon, even if you had all the time in the universe, that none of the other elements would actually be able to do the job carbon does. The other question is, could life have been based on a non-carbon set of elements? And that is a big question. I mean, there's science fiction about silicon-based life. I think there's good arguments about how under our normal temperatures and pressures, that could not happen. So what I'm going to say is, for water-based planets, and I think water is the best solvent that you can have for liquid flow. You need to have gas, liquid, and solid going on. When you think about all the things that you need, you can say maybe in this minor way this one element could be used differently. But the way it all goes together, I think that you can't really move away from this in a major thing just because there's so many things that you need. You need three phases of matter. You need the ability to make lots of different shapes from that matter. That's one of the things that carbon may be uniquely good at. And you need the flowing system of water to be able to dissolve things, move things around without losing them out of the atmosphere, which is, by the way, the next question that we're going to have. So the one thing that I think that you might be able to get away from, maybe you'd be able to build something based on formaldehyde rather than water. It's a different kind of ocean. I think that would still be based on carbon, number one, and I have to see a formaldehyde planet before I believe that you could have an entire formaldehyde ocean. And I think you need a planet-wide ocean to be able to have the liquid phase that you need. So that's why I'm going to say, other than carbon, almost certainly not. Other than water, maybe a little more, but probably not. Show me the planet that's going to replace water, the liquid on a planetary scale that's going to replace it. That's why I talk about Titan when we talk about that in chapter 4. It's going to talk about methane as a possibility. So again, keep this in mind. The really off-the-wall thing where there might be totally new chemistry would be plasma, the fourth phase of matter that is present in the middle of a sun. That's what I would actually think about, if an alternate system that would develop in the plasma heart of a sun, using the flowing plasma to be able to develop this kind of thing. And there's problems with that. I can't imagine it, but that's so different, and yet it does seem to check more of the boxes. So I would say not even a different set of elements, but a different phase of matter. Yeah, but I still doubt it. But it's a fun thing to talk about, that's for sure. So here's a question about the atmosphere. This is actually a little bit related to the other ones. Hazen, and the geologists, the geology way of looking at things, it looks at the atmosphere, and remember that geology actually includes the whole Earth. So atmosphere is a form of geology that you can look at. Geologists study how the atmosphere interacts with rocks and things like that. And there's the idea that gaseous elements slipped into space. How would that occur? And why would we not need to be concerned about that anymore? It's very different, but it seems like this is something to worry about. Well, the good news is you don't really have to worry about this anymore, because a big factor to what holds the atmosphere in place is gravity. So the fact is the lighter elements are the ones that are more likely to escape into space, and it's why hydrogen escaped into space. It's why you have so much hydrogen on that last graph, that you have so much hydrogen in the universe, and yet you don't have as much of it on Earth. You still have a lot, but it's not the majority element by anybody's measurement. It's actually able to escape into space, and because of that, we actually have a more diverse set of elements instead of being 75% hydrogen or whatever the universe is. So that's actually good to lose the hydrogen because there's so much of it. And hydrogen mostly leaves. Helium actually leaves, and it's one of the reasons why it's hard to find helium. You have to find it where it's been sort of trapped in rocks. And then you get down to things like carbon, and that's carbon dioxide. And those things are heavy enough to where, number one, they're held down more. And also, there are ways to replenish those that are different from the smaller elements like hydrogen. So there are some replenishing processes from biology. That's photosynthesis. That makes oxygen. It replenishes the oxygen and increases it. So that's a big example. We don't have to worry about oxygen leaking away because, in a sense, the system could dynamically change to produce more oxygen from because that's what it already does. And there's also gases that come out of the molten core. Now, there's huge questions about where exactly, how many gases, where they come from. And I'm just going to say gases actually move into and out of the core of the planet as well. So the ones that go into space are lost, but the ones that go down to the planet are sort of saved. And because we have so many of these processes, and gravity is also helping us, that's why, other than hydrogen and helium, we don't really have to worry too much about the lighter gases leaving and not coming back, because there are ways to replenish it. Remember that we had that one figure about photosynthesis at the end of our textbook, chapter 2, that talks about the flow of energy into the earth. You can think of doing something like that for the flow of oxygen. It's why I like our textbook, because you can see that those flows are important to this exact question, and that's also, they're not normally in physical chemistry textbooks, but guess what? They're in ours. And so I'm liking our book, and I'm glad that we're going through it. This is just a picture. This is actually from R.J.P. Williams himself, one of his books that shows how the crust circulates. The crust is actually, it's a solid, but it melts and it goes into the core. As it does that, it actually takes ocean water and even some gases down into the core. And then there's dissolved gases that have been in the core for a long time, since the beginning in some cases. And those gases are released when that comes out at the edge. In fact, volcanoes will actually be outlets for this gas. So when a volcanic eruption happens, you actually can have worldwide changes in gas concentrations. Pinatubo was one of them, and there was a big eruption that even changes the climate a little bit. And so that's why I have this picture here off to the right, because I've used this in a talk before, talking about how all these things relate. They co-evolve, to go back to the first question, and they actually dynamically dissolve with each other. Flows are the basic thing that we're talking about. These are not at equilibrium necessarily, but they can be at a steady state. A steady state, not at equilibrium, because you have an inflow and an outflow that match each other. They're going to different places, but they match each other. And so that makes, a lot of people have looked at this before, and they've called the Earth a giant chemical reactor. I even had that in a talk, and I have sort of a picture of a giant chemical reactor over here that humans build, and there's a giant chemical reactor over there on the left that is natural. And yet the chemical reactions make things happen, but it keeps the stuff in place. And there are forces like gravity that keep the gases in place, and there are other forces that replenish them. It's really complex exactly what those forces are. So again, good questions to keep in mind as you run through. Now for the biggest one, there was even a little parentheses of, I hope this isn't too much. And well, guess what? It's not too much, because I want you to be asking these questions. On page 32, there's an actually very important statement in the book that Williams' hypothesis was based on chemistry, that change was not only dramatic, but it was inevitable. The pattern of change that we have is inevitably towards oxygen. That's even a stronger word than I like to use usually, but Williams was not afraid to use it. Chemistry determined the first conditions on Earth and then changed over billions of years. Now, this says, I'm pretty sure you are a theist. And by the way, I didn't make you read this, but in the author's note, I actually sort of come out as Christian at the very beginning, because I want people to know that. So if you missed that, check out the author's note just to make sure that you know that all my cards are on the table from the beginning. And even R.J.P. Williams, he was not a Christian. But I have a report, and again, this is basis of rumor. This is not scientifically proven, but this is never scientifically proven. These are outside of science. Near the end of his life, he was talking with a Christian scientist who was talking about just how the order and how wonderful the order was that he found in the universe. And he said to that person, Alistair McGrath, he said that he saw so much order in these things, in these inevitable processes, as he took it, that he was thinking that maybe God did it. And then that was very near the end of his life, and it's just a rumor, but to me, these patterns and these order give the evidence of an ordered universe, and that is actually an important part of the theology of creation. Says that the creation of the universe was ordered into 6 days. And I'm not going to align those 6 days in Hebrew with the phases of the earth, but I'm going to point out that the main thing is that they were ordered at all. A lot of the creation narratives don't have that much order to them. And so actually I see Christianity as seeing the order and attributing that to God, saying that God is like this. God has orderly, but also gives us freedom. And so we have these layers of order and freedom that occur. And actually theologians all through the centuries, I've just been reading one from the 4th century, that his basic question was about this. And he looked at Genesis and he drew conclusions that I actually find very interesting as a scientist today. Not about the science, but about the theology, which is the more important thing to the theologian, right? So, my author's notes there. When you get to chapter 12, I'm also going to lay more cards on the table. I'm going to say some more about philosophically what does this mean. And I'm only going to get to the philosopher's God. I don't know if I even mentioned the word God in this book. I intend not to, because I want to talk about nature, and then I want you to think about it. And I want you to think about what it means. What I want to say is that chemistry is never a substitute for God the Creator. If the Creator made chemistry, then the chemistry is doing the Creator's will, right? The chemistry is a servant. It's a secondary cause. As one scientist put it, I think that chemicals even caused the origin of life. But they did so because they are God's chemicals. You know, the chemicals belong to God. If all the sheep on the hills and all those. So you can have verses about this. There's a whole big thing. And again, this is a big question, but I do want to honor it. And I want to say that it's such a big question that I actually have been writing about it and trying to work this out myself. The biggest thing I want to say is that God as creator does not exclude certain mechanisms of creation. And there's lots of people who think that. If you think that, then I would say that the picture of God that excludes that is too small. It's not really the picture of God that, say, Thomas Aquinas talked about, or Augustine even. And if we look at the picture of God that Jesus presented, Jesus talked about lots of natural things that we have natural causes for. And he said God is the ultimate cause of those things. So there's lots to talk about here. But I just published an article because I've always felt a little bad that I've written this as a science book for a science audience. And therefore, I can't assume that you even know we even agree on what the word God means. You know, theologically, I couldn't introduce theological terms. The science was hard enough. But I wanted to deal with these questions on a scientific level and open the door to other disciplines as well. And I always had this idea that maybe someday I would write an article that sort of explained it. Well, guess what? Just this year, I've just published that article. And this is what it is. It's in a journal of a association that I'm a part of. That's a bunch of scientists who are Christians who talk to each other about science and theology. And I want you to notice this right here. You're probably thinking of nature as a watch, you're thinking of it as a mechanism, as the chemistry, and we do have mechanisms in chemistry, right? But I want to say that that's great for some things, but it can run up against limits, especially when we're asking questions like this. So this whole article is arguing against the idea of God as watchmaker, because God as creator. The universe is not a watch. A watch is just one metaphor among many. And so I want to say, if the universe is not a watch, what is it? Well, it's a chemical process. And what does that mean? So this is the first sentence. We've had the central metaphor of nature as a watch. It's colored the debate about natural theology since Paley and Darwin. Both Paley and Darwin, and I explain who they are in the thing. However, a chemical interpretation of natural history will differ, because chemical systems do not work like watches. We're talking about how they work in this class. What does it mean? Well, that's a little bit outside this class, but I welcome the question now, and I welcome you to read this article. I'm going to read a little bit from it just to show you why I think that this moves beyond the metaphor of nature as this big mechanism that is a watch that doesn't need God to do anything for it except to wind it up and let it run. Theologians have always disagreed with that. In fact, if you think about it, what did theologians think about creation before watches were invented? Well, they had very different metaphors. And those metaphors are actually helpful. That's why I'm trying to excavate with this particular thing. So I want to go back to theologies from before the invention of the watch, that they were ancient and medieval views of God, and they can refresh our current understanding of creation. And in many of these, God's not seen as a hands-on artisan who makes the world like a watch. God is seen as something even more involved with the world and even more close than that deistic idea actually implies. Here's my key paragraph. The metaphor of nature as a watch has limited our discussion of creation to mere complexity and bracketed out its goodness and beauty. So I want to focus on its goodness and beauty here. How do I do that? Well, I talk about how chemistry is good and beautiful, and I talk about how that creates new things, which is an act of creation. I'm a chemist who makes proteins and not watches. I nevertheless see in nature many chemicals, bright and beautiful, which are irreducibly novel, even if reducibly complex. So in my book that you've been assigned to read, I described how chemicals in natural history have dissolved, melted, mixed, and precipitated throughout the narrative of evolution. And here in this article, I give a theological interpretation to that story by identifying its moments of irreducible novelty, looking at creation not as a watch in a field of grass, but as chemical structures and systems on a planet in a field of stars. And so I will post that. It's not a required reading for this class, but if you asked, I've got my answer of a sort in this article. So thank you for your very good questions. I hope that this gets us pointed in the right direction. And keep thinking about what questions you're going to ask as you read the next 3 chapters. We'll have that due in a couple weeks. All right. Thanks for your time.